my first time to Russia, and it's quite an impressive turnout. We had our first London Cassandra conference last year, and there's at least as many people here as we had in London, so very impressive. Lots of smart people in Russia, and good to have some of those minds looking at Cassandra. I've been working on Cassandra for about 5 years, and we started off in kind of the social media niche where we had Facebook and Twitter and Reddit, early Cassandra adopters. Today we have thousands of companies using Cassandra in all kinds of industries. I want to talk about just a handful of those that are a little bit representative of what people use Cassandra for, to give you an idea of what problems Cassandra can help you solve. The first of those is eBay. eBay uses Cassandra in several of their applications, including the Red Laser analytics tool, as well as every time you are on an eBay page and you want to manage items that you like or that you own, or that those are all tracked in Cassandra as well. So eBay selected Cassandra because of a number of reasons. Among those reasons are that Cassandra is very good at dealing with time series data. So by time series data, I mean anything that has a chronological component to it. So we have on the left monitoring data from managing a cluster of machines. At the top we have user activity on a website, and at the bottom we have financial activity. So all of these are examples of time series data, and there are companies using Cassandra to deal with all these types of time series data, as well as others. Another thing that eBay appreciated about Cassandra is that Cassandra's support for deploying across multiple data centers is the best in the industry. So you can have, in this diagram, what I've tried to show at the top, and we have some data centers in the cloud. At the bottom, we have data centers that are traditional on-premise clusters of machines. And Cassandra can span a cluster across all of these. It can be very heterogeneous, whatever you need to support your application. We've also done some work to make sure that Cassandra is efficient across these data centers. I'll talk a little bit more about how replication works locally, but when we replicate across a data center, we'll actually just send, if I want to have 3 copies of a row in a remote data center, I'll actually just send 1 copy across the WAN, and then the replica that receives that will then forward it to the others. So we have a lot of experience at this point working with this situation and optimizing for it. In fact, Axel from Spotify, who will be speaking later, his team has actually done a lot of the work to make this solid and robust. Another reason eBay chose Cassandra is support for distributed counters. This is actually an interesting problem because of the support for multiple data centers. If you just have a single data center, it's easy to support a counter data type, because you just say, this replica will be in charge of counting this object, and then everyone sends their count operations to that replica, and it works great. Most systems operate like that. But when you're in a multiple data center environment, you can't afford the latency on every operation to go and talk to a single master replica. So what I've tried to illustrate here, and it's probably too small to see in the back, but what we do is for for each counter, we'll split it into a number of partitions corresponding to the number of replicas that we have for that counter. And then each replica will then be responsible for a third of the operations if I have 3 replicas. And then they'll replicate to each other asynchronously. So what this does is it lets me perform increments with local latency and then forward those replication operations across to different data centers asynchronously. The final reason that eBay likes Cassandra and chose to deploy it on Cassandra is good support for Hadoop. So Hadoop is a complementary technology with Cassandra. They work well together. What Cassandra lets you do in particular, besides just allowing Hadoop to perform MapReduce jobs against the data in Cassandra, it will let you create a deployment scenario like this one, where I have the Cassandra real-time nodes in blue, and I have workload separation from the Cassandra nodes that are serving the Hadoop workload in green. So Cassandra's replication can treat this as if I had 2 data centers and replicating between the 2 of them asynchronously. So that means that when I spin up an expensive, long Hadoop job, it doesn't crush my application while it's doing those sequential scans. It's separated onto different machines. Another company using Cassandra is Adobe. And they're using this to support basically analytics in the cloud for their customers. Adobe also has a number of different reasons why Cassandra was a good fit that are similar to eBay's reasons, but some of them are distinct. Adobe in particular was concerned about low latency, and they want to make sure that their queries are completing quickly. This is a graph of an anonymous Cassandra user from a production cluster, and they are getting half millisecond, 95th percentile latencies. So that is to say, 95% of their read requests complete in under half a millisecond. Again, this is not Adobe. This is someone else anonymous, but you can achieve those latencies with Cassandra and achieve them with a high degree of confidence. Adobe was also concerned about scalability. The application they built on Cassandra was a new one, so they wanted to make sure that Cassandra could grow as the customers grew. And so what I'm going to try to illustrate here is how Cassandra adds new capacity to the cluster. So each of these 5 initial nodes in the cluster manage a certain amount of data that I've represented with these little boxes inside the node. So those correspond to what we call a vNode. vNode stands for a virtual node. And what this does is when I add the new node to the cluster, I can pull small numbers of vNodes from each of the existing nodes. And so by doing that, I'm spreading the impact of adding that new node across the entire cluster. So I'm not imposing harsh demands on just 1 or 2 nodes, but I can spread that across the entire cluster. So especially as you start to talk about larger clusters, this starts to become more meaningful in how smooth I can turn that scaling operation. Another thing that's related to being able to scale like this is actually being able to do upgrades. So one of the things that Cassandra is unique in is our focus on upgrading without downtime. So if I'm going to upgrade my Cassandra cluster to 2.0, I can upgrade one node at a time so that the entire cluster is never down. I can keep my application going during the upgrade process. Another thing that Adobe cited was Cassandra's support for tunable consistency. And I'm going to have to give a little bit more background about how Cassandra replication works before we dive deep into that, but we'll keep that in the back of our minds and come back to it. The third Cassandra user I wanted to highlight this morning is Instagram. They use Cassandra both for logging and also for their notification service. And again, they have some specific reasons why they chose Cassandra for this, some that are shared with these other users and some that are unique. One that architecture, and by right I mean W-R-I-T-E, not correct. So in particular, that Cassandra not only supports replicating across the cluster, but even on a single machine, Cassandra writes are durable. So once Cassandra acknowledges the write, then it won't be lost, even in the case of a power outage. So the way we achieve this is with a log-structured storage engine. So here's a quick overview of how a write works in Cassandra. When the client sends us a request to a specific replica, the first thing we do is we'll append that to the commit log. So that's what makes it durable. So before we do anything else, it's appended to the commit log. That's almost free because we're not doing random writes. We're just appending to a commit log segment that we've pre-allocated. So even the journaling is free because our commit log segments are a fixed size. So we don't even have to sync metadata on that. We just need to append the actual row that we're updating. And then what we'll do is we'll store the update in a structure called a mem table. So the mem table is a memory-based structure, and what happens as we go through and we send more writes to it, and the mem table starts to fill up, we will write that mem table out to disk, and at that point we can go in and we can clean up the commit log and say, hey, I don't need those rows that you wrote to the commit log because they're now in a structured data file on disk. And so since we're doing appends in the commit log, and then we're doing a sequential write all at once on the mem table flush, we never have to do random writes. So on spinning disks, that means that we're never doing seeks, and on solid state disks, it means we have really low write amplification. So this is why Cassandra can deliver the write performance that Instagram needs. Instagram says that since they've migrated to Cassandra, they have 99.9999% uptime. So pretty good numbers. And I'll talk a little bit more about how this works. So just to summarize why people use Cassandra, I think these are pretty good summary that scalability, performance, ease of use, and availability. So I want to drill down just a little bit into the performance side. Last year at the Very Large Databases Conference, some researchers from Canada did a benchmark between Cassandra and some other databases. So they used MySQL as kind of a control, a known quantity, and then they also benchmarked HBase and Redis, and this was their result. So the interesting part about this is that this is a reads, writes, and sequential scans workload. So I'm mixing different kinds of operations into this workload. So down here at the bottom, this is MySQL. So that's the reason MySQL has so much trouble with this is that it is a mixed workload, that you have all of those different kinds of operations contending for the I/O. Cassandra's log structured storage engine allows us to reduce the contention considerably in this workload. So Cassandra scales nicely linearly with the number of nodes in the cluster. But there's one problem with this benchmark from my perspective, which is that when I tell people that I work on a NoSQL database, then they ask, well, how does Cassandra compare with MongoDB? Because a lot of people have heard of MongoDB, and the Canadian researchers didn't actually include MongoDB in their benchmark. So DataStax actually hired a company to repeat the same benchmark, but to include MongoDB as well. So notice that the reason why it's curving more than linear is that I actually have a logarithmic scale here. So unlike this graph where I go 2, 4, 6, 8, on this graph I'm doubling at each point in the graph. So that's why it looks different. So you have Cassandra still about 4 times faster than HBase. So we're basically getting the same result that the BLDB guys did. So that makes us feel pretty good that what we're doing is reproducible. And here's MongoDB at about 18 times slower. So there's a number of architectural reasons for this. One is MongoDB's global write lock. So when you have a mixed workload that mixes writes in, then that does lead to a lot of extra contention. And then MongoDB also has a memory mapped based storage engine. So it tends to do poorly with workloads that are larger than memory. And the amount of data in this benchmark is about twice as large as memory. So I did tell Endpoint, I said, make sure you benchmark with more than memory, because I knew this would happen. What we've been focusing on in 2013 is ease of use. And we want to make Cassandra more familiar and reduce the learning curve for people who are new to Cassandra. So we created a language called CQL, so Cassandra Query Language. All of the statements on this slide are valid SQL as well as CQL. So these statements are valid Cassandra statements. So you get select, from, where, you have indexes. The main thing you don't have is joins. And the reason you don't have joins is that Cassandra is built to be a distributed system. And doing joins across machines is a great way to get terrible performance. So we don't support joins. We encourage denormalization instead. This is a good summary of some experiences using Cassandra and how Cassandra's helped them deliver the reliability that they need. At the bottom here, Nathan Milford. So a few months ago, Hurricane Sandy hit the east coast of the United States. Nathan's company, Outbrain, lost an entire data center when that happened. But because Cassandra's replicating across data centers, they were able to fail over to the other one and keep on going and repair after the other data center came up online. In the lower right, Jake Luciani, Cassandra dealing with losing individual disks. So we handle failure at a machine level as well as at data center level or at a cluster level. So I want to talk a little bit about how Cassandra is designed to offer this kind of reliability. So this diagram is what Cassandra is not. So this is what you end up with typically if you have a MySQL database or maybe a SQL Server database and you outgrow it. So you say, okay, I'm going to shard it. So I'll have a bunch of different shards. Each of the shards will have a master that replicates to some number of slaves. If the master goes down, we'll fail over to one of the slaves. We'll promote that to master. We need some router in front of the cluster telling clients which shards has the data they're looking for. So the router, incidentally, is another single point of failure. We'll need to do some effort to make that redundant as well. So there's a couple problems with this design. One is that the master-slave design is inherently failure-prone. So if for instance, suppose that the master here is unable to talk over the network. It's still alive, but it can't talk to the other machines in the cluster. So the other machines will elect a new master. And now suppose the network heals, now I have two masters. That's not a situation that we're designed to deal with here. So this sounds a little theoretical. This is actually very similar to the architecture that MongoDB uses. And people have actually seen this happen in production where they ended up with multiple masters for a MongoDB partition and all hell broke loose. It's an interesting talk about that. I'll get the slides online. There's a link with more information and another follow-up link on how to deal with network failures. So what does Cassandra do instead? Cassandra has a fully distributed replication model where any node in the cluster is able to route requests to the correct replicas for a given row. So in this diagram, I have the client in the upper left, and it can talk to any Cassandra node, and which can then route those to the correct replicas. So if this node that the client is talking to fails, the client can just pick any other node in the cluster to reconnect to and pick up where it left off. So how does this work? Cassandra uses something called consistent hashing to determine which replicas should own a given row. And what we'll do is, for your row, we'll look at the primary key. I have an asterisk here. That means that it's actually just the first column of the primary key that we look at. But for the simple case, that's just the entire primary key. So we'll look at our primary key, and we're going to hash it into a fixed token space. So by default today, Cassandra uses the murmur3 hash, 64-bit hash. In the past, we've used MD5. We don't need cryptographic hash properties. All we really care about is getting a nice, even hash distribution, and we also care about speed. So murmur3 is a good fit for us. So the way this works is we're going to not just hash the primary keys into a 64-bit hash space, we're also going to assign 64-bit tokens to each machine in the cluster. So if I have a 4-node cluster, I might assign them these tokens, and then once I've hashed the rows, I can just do a binary search against the tokens in the cluster to determine what machines each row belongs on. So this lets us pick a single replica. So then the next step is, how do we go from a single replica to multiple replicas? Well, the simplest thing we can do is we can just walk along the token ring and say, okay, you're going to be the next replica, you're going to be the third replica. In practice, Cassandra gets more sophisticated with this. I can tell Cassandra what racks each machine lives on, and then Cassandra will try to replicate things so that each rack has at most a single replica, which will let us avoid correlated failures when a power circuit gets overloaded and I lose the entire rack, or a router dies and I lose connectivity to the rack, or a cooler fails and machines close to the cooler start overheating. In practice, there is a physical component to failures. They're not entirely random, and Cassandra lets us respect that when it plans its replication. So I've been talking about the case where I have a single token assigned to each node. I mentioned earlier that we have something called virtual nodes. What that means is we actually have multiple tokens assigned to each node. But the consistent hashing concept doesn't change. It just means that it's a little more complex under the hood. So I want to look a little bit deeper now at what happens when I do a read request. So again, I'm going to have, the client's going to be talking to some node in the cluster that doesn't necessarily own the data that we're reading. So that node, we'll call that a coordinator. It's going to coordinate the request for this client. And we track the performance of the different replicas in the cluster, and we can route that request to the replica that's least busy. And then that replica will reply to the coordinator, and the coordinator will forward that back to the client. So this is simple, right? Everything works fine when nothing breaks. Let's look at what happens when something breaks. So again, the coordinator is going to send a request to a replica, but the replica has some kind of failure, and it doesn't reply. And maybe it's because it died, maybe there was a network problem, maybe it just hit a Java major compaction and had to stop the world while it cleaned up its heap. So whatever the reason, we don't care what the reason is that it failed. All we care about is that it didn't reply as fast as the coordinator expected. So what the coordinator will do is it will retry that request to another replica and then finish that process of giving that data back to the client. So we call this, when the coordinator fails over to another replica, we call this rapid read protection. So this is a graph of what happens. This is a 4-node test cluster, and right at this point, we killed one of the replicas. And you can configure rapid read protection with how aggressive you want it to be, how eager you want it to be to retry the requests. And the reason is that the more requests we retry, the more extra work the cluster does. So you can see here, this is the bottom line here. This is retrying each request to a second replica. Even if nothing fails, I'm always going to do a redundant request to make sure that I get my answer. And so you see that the throughput, when everything's going fine, the performance is lower. So there is a penalty associated with doing that. Conversely, if I'm not doing any retries, then my performance is great, but then when I killed the machine, then a lot of requests timed out and failed. So by default, we'll retry at the 90th percentile, 99th percentile, which means that the slowest 1% of requests will retry those. You can configure it either by percentile or by just a fixed retry after this many milliseconds. Either one of those is acceptable. Or always, yes. So far I've been talking about just reading from a single replica. This is called, in Cassandra terminology, this is called reading with a consistency level of 1. So we can also tell Cassandra, I want you to check more replicas to make sure you have the latest version of the data. So in this case, I'm going to check 2 of the 3 replicas, which is called a quorum read. Consistency of 1 and of quorum are the 2 most common options to use, because both of those allow for at least one machine to fail while still being able to complete the requests. I can also have I can request a consistency level of all, which would mean I need to check each replica. But if I'm doing that, then as soon as I lose one replica, then I have to tell the client, sorry, I can't service your request. So 1 and quorum are a lot more popular. When I'm checking, when I'm using a consistency level of quorum for both reads and writes, then I'm guaranteed that I'm always going to see the most recent version of the updated row. So we have the, besides 1 and quorum and all, we also have local quorum, local 1. What those are saying is, if I have multiple data centers with replicas in each, then I only care about a majority of the ones in my same data center, and I'm okay with ignoring the ones in the other data center. I'm okay with doing those asynchronously, which means I'm giving up a little consistency in exchange for better latency. You can also use a consistency level of 2, which means any 2 replicas, maybe they're in my same data center, maybe not. As long as I can write that to 2 replicas, then I'm good. I'm happy. I'm confident that my data is safe even if I lose a machine. So these consistency levels are what Cassandra offered up until the most recent release of Cassandra 2.0 this past September. There are some problems that you can't solve even with strong consistency of quorum writes plus quorum reads. So let me give you an example. Suppose I'm dealing with user accounts in my application, and I want to allow users to request a specific username when they create an account. So if I have 2 users simultaneously, or close to simultaneously, trying to create this account, what I'm going to do is first I'm going to ask, does this account exist? If it doesn't, then I'm going to create it. So fair enough, right? So first user says, does it exist? Cassandra says, no, it doesn't exist. Meanwhile, second user says, does it exist? Cassandra says, no, it doesn't exist. Meanwhile, first user is doing his insert. So since Cassandra told the second one it didn't exist, then he's going to insert it as well. So this record is going to get overwritten by this one. So even if I'm using consistency level all, this is still a possibility because there's no locking between these two steps. So locking in a concurrent system is a dirty word. We don't want to have to. We don't like locking because A, it means that there's a high degree of contention, but B, there's the whole question of how do I clean up a lock if the client who created the lock fails himself. So we had some experience in the Cassandra community of people using systems like Redis or Zookeeper to create a lock manager. But it gets messy very quickly when you have those locks in a distributed system where machines can fail. So our solution to this was not to give you locks, but to give you what we call lightweight transactions. So what we do in this example is we added a clause to CQL, which is the if clause. So I can say if not exists when I do an insert. And that makes the check and the insert atomic. So Cassandra will say to the first one, if he says insert if not exists, Cassandra has a special column in the results set called applied. And the brackets are actually part of the column name. And it will say, yes, it was successful. The next one, who says create if not exists, he'll get back apply to false, but he also gets the rest of this. And what that is it's the row that exists. So you said do it if it doesn't exist. So I'm going to tell you not only that, hey, it does exist, but here's the row that exists, so now you can determine what you want to do based on that information. So besides creation, you can also do lightweight transactions on rows that do exist, and you can say, apply this update if this column matches this expected value. So we implement this using a consensus protocol called Paxos, which is a good match for Cassandra, since it does use quorum-based operations, which means I still can lose some number of machines from my cluster, and as long as I still have a majority, I'll still be able to make progress. I'll still be available to my application. There's an article called Paxos Made Simple that describes the approach we use. Most Paxos implementations are concerned about creating a distributed write log, which is actually a little bit different from what we do in Cassandra. So we're not doing multi-Paxos with leader election. We're doing the bare minimum to keep it simple and to keep it reliable. The downside is that we require 4 round trips for a lightweight transaction. So your performance, you can expect your performance to be roughly 25% of what ordinary updates are. And that's if you're in a single data center. If you're across multiple data centers, then you're paying that latency penalty to coordinate with the replicas in each data center. So you can see how in a situation like user account creation, I'm okay with paying the latency penalty to make sure that I am the only one creating that account. But for most operations, you're going to want to use the normal consistency level based approaches to get that asynchronous property of the replication. I have a post with more details about how this works under the hood, and another link to an excellent talk about dealing with, building applications with an eventually consistent approach. So I have a little bit of time to talk about what's coming in Cassandra 2.1. The two main features from an application developer's perspective, the first of which is user-defined types. So what that looks like is I can create a type. So here I created an address type that has a bunch of fields in it. Note that the phone numbers field is a set. So I can have a set that is part of a type, and then I can use that type in a map. So this allows me to have nested collections. If you've been following Cassandra for a while, you know that we added collection types at the beginning of January. So we added maps, we added sets, we added lists, but they're not nestable. They can only contain primitive types. So this lets us make that much more powerful. And now I can have a map of addresses that in turn contains arbitrary fields as well. So this is here I just have a nesting of 2 levels deep, but it's arbitrarily nestable. There's no limit on that. So what this means is I don't need an object relational mapper. I can just say whatever structure my data has in the code, I can just correlate that one-to-one to a Cassandra row and have that nested as needed. So then we added some extensions to the CQL language to deal with that. So we're just using using a dot notation to represent fields inside of a column. And then the next thing we're adding is along the same lines, which is extending indexing to collections as well. So in this case, I have a set of tags, and I want to index that tags collection. So then I'll be able to say select from songs. This was actually a proposed syntax. The syntax we ended up going with is where tags contains blues. So we added a contains keyword, and then you get back this result. So from the user perspective, the big features in 2.1 are making collections more powerful. From an operations perspective, I think the thing that's most exciting is more efficient repair. So you recall that as updates come into Cassandra, we fill up a min table, we write out data files called SS tables, and eventually we're going to have many of these data files. So when I go to Cassandra and I tell it, I want you to repair yourself, which means I want you to compare the data for all the replicas of this token range and make sure that they all contain the same rows. So what we do is we'll go ahead and we'll take that data, we'll build a Merkle tree, and my Merkle tree diagram died. So that didn't work. What we'll do is we'll create a hash tree. I'll look at the rows in here, and I'll hash those rows, and that will be a leaf of my tree. And then I'll go through another set of rows. That will be another leaf. And then I'll take those 2 leaves, and I'll hash those together, and that will give me an intermediate node. And I'll build that all the way up to a fully populated binary tree. So it's the same idea as rsync applied to databases, which is that if most of the data is in sync, then I shouldn't have to transfer a lot of data over the network. All I need to, in Cassandra's case, all I transfer is the head of the tree, and then if those match, I know I'm good. I know everyone has the same data. if they don't match, then I'll drill down into the left child and the right child so I can find out where the difference is coming from. And then I'll re-replicate the data in that leaf of the tree. So the problem is that we are rebuilding it, and let's see. We are rebuilding that based on the entire data set every time you do a repair. So you can see how when I'm getting into the multiple terabytes of data per Cassandra node, that starts to get painful. So ideally, what we'd like to do is we'd like to build that based on just the new data since the last time we repaired. If I know that I've already repaired this data, then I shouldn't have to do it again. I should be able to just say, just re-repair this new set of data. So this makes repair dramatically more efficient, much less painful to do in a production cluster. Some of the other things coming in 2.1 are some work to make managing cold data sets more efficient. So Cassandra will dynamically scale back the granularity of its indexing of cold data. We're rewriting counters to make it more robust. And we're planning to deliver this in late January, early February of next year. So in 6 to 8 weeks. We have some time for questions.
How do you compare to Basho's React database in terms of performance?
React is probably the most similar to Cassandra architecturally. I'd say the biggest difference at an architecture level is how the cross-data center replication works, where ours is better. But in terms of performance, Cassandra is about 4 times faster. So it's significantly faster.
All right.
Thanks for your speech. Tell me please, when you said about read latency less than 1 milliseconds, did you mean that all your data located only in memory? Or you mean that your data was located in memory and in hard drive too?
I'm sorry, his mic's cutting in and out. You might just want to yell the question.
Раз. Okay. When you said about okay, when you said about read latency less than 1 milliseconds, did you mean that all your data located in memory, or it locates in memory and hard drive?
So the question is, my slide where I showed a Cassandra cluster posting sub-millisecond read latencies.
Yes.
Is that a memory-based workload? That cluster has a data set larger than memory, but it is deployed on solid-state disks. So it does have that advantage.
Do you have some adapters for SSD in Cassandra?
The question was, is there a special adapter for SSDs? We use the same storage engine for both hard disks and SSDs. The main difference is that SSDs do give you better random read performance.
Thanks.
You told us about failures of data nodes in the cluster. What about when the coordinator dies?
When the coordinator dies, it's up to your driver to handle the failover. So in the Java driver actually will do token-aware routing by default, which means that it will send the request to a coordinator that is also a replica. So that's not mandatory, but sophisticated drivers will do that to reduce the latency further. But what all it will do is it will just fail over and retry the query to a different coordinator, and it does that transparently to your application. And there's an execution state object that you can inspect if you need to know, did you need to fail over? Who did you fail over to? So that information is available, but we tried to make it so that it does the right thing by default, and you don't have to worry about it for the most part.
Do you have any plans to use SSD advantages, when flashing is stable?
Sorry?
Advantages. SSD has good random access. So when flashing is stable in disk, you can use.
So the question is, are we going to do anything to exploit the good random write performance you can get from SSDs? Probably not, because of write amplification. So even though SSDs are faster than hard disks at random writes, it's actually about an order of magnitude slower than doing sequential writes on an SSD. Because if I update a 100-byte row in a random write, then the SSD under the hood, it needs to actually read a whole block and then change that 100 bytes and then write that entire block back to the disk. So you're actually still giving up a fair amount of performance there. So in the near future, at least, we think that the log structured storage engine is still the way to go.
How do those user-defined types look on the client? How do they look like on the client? Python, Java, when I select the account with address, how does it look? Is it a map or set?
Do you know the answer to that?
Yeah. I'll answer in Russian. Клиент должен это делать. То есть в метадате передается... В метадате, который возвращается к клиенту, сейчас дается полное описание типа, раз. Значение присутствует, как оно хранится в базе данных, то есть в виде глоба. То есть это дело клиент должен уметь разбирать. Но вместо данных достаточно данных для того, чтобы это дело разобрать. То есть нужна клиентская поддержка в драйвере. Пока нет, это версия 2.1, так, она еще сама по себе не вышла. Текущие DataStax драйвера, они все ориентированы на 2.0, так что пока нет, но в течение пары месяцев, нескольких месяцев будет.
И последний вопрос.
Thanks for your talk. You mentioned Cassandra query language, and one of the benefits is promotion of Cassandra for regular SQL users. Are there any other benefits?
Yeah.
Especially for users who use Rift as basic protocol.
Well, I think the advantages for people coming from Thrift are primarily that it allows us to do more sophisticated features like lightweight transactions are easy to do in SQL, and nested types. Even collections is something that you can't really make sense of from Thrift. So really it's about having a foundation to make the development model more robust. That said, because we've also been able to create a native protocol for CQL, that's asynchronous by default, that uses prepared statements, you can actually get performance advantages as well. But the main reason we want to do it is for just the development experience.
And my second part of the question is how to update collection values. So if I, in Thrift basics, some people emulate collections, so by naming of the columns and so on. And here, if I don't know how columns are named, so I'm not sure that I need to use particular protocol, how I can add value to this collection.
Are you asking how to add values to a collection from Thrift?
Yeah, from Cassandra query language. I have initial collection with 2 values, and I want to add 1 more.
So for instance, I have
Yes.
a set.
Yes.
So what I would do is I would say, update songs, set tags equals tags plus, and then new values. Then where the row is such and such. So I can append to it without knowing the existing value.
And how conflicts will be resolved if 2 clients do the same thing?
It's similar to conflicts on a field that's not a collection. So if the elements in this set are unique, then they'll get merged and both of the updates will happen. And actually a set's a really good example because if I add duplicate values, then the set just throws them away anyway, it doesn't matter. The more interesting question, I guess, is for a list.
Yeah.
So list is where you can get into trouble because I will allow you to say update, set, and I can set a specific index inside the list. So if I have 2 people updating a single element inside the list and they both said I want element 4, then you have the same situation where one of them will win, one of them will not. So appending will never have conflicts, but if you say I want to update a specific element, then you have the potential for conflicts.
Sense.
Thank you, Jonathan. Благодарим докладчика.